So imagine you're writing this, deeply personal, just heartbreaking letter to a friend.
Okay.
You pour your entire soul into these words, right? You fold the pages up, slide them into a cardboard box, tape it shut, and you hand it over to a postal worker.
Yeah, standard stuff.
Right. And to you, that box contains like your deepest, most vulnerable truths.
Yeah.
But to the postal worker, that box is literally nothing more than a 3-pound rectangular prism.
Exactly. They don't care.
They really don't. Like the postal worker doesn't care if the box holds your love letter or a stack of blank printer paper or even a pair of shoes.
Right, because their only problem is an engineering one. Like, how heavy is it? What are the dimensions? And where is it going?
Exactly. And that separation, that complete, utter divorce of the cargo's meaning from the physical mechanics of its delivery, that is the conceptual leap that basically built our modern world.
It really is. I mean, it's the core premise of Claude Shannon's 1948 paper, A Mathematical Theory of Communication.
Which is exactly what we are getting into on our deep dive today. So, welcome everyone. Our mission right now is to explore this foundational blueprint of the whole digital age. We are unpacking the source material that made the internet, Wi-Fi, digital cell networks, all of it possible.
Yeah, we're really getting into how information itself was, mathematically defined and quantified.
Right, and packaged. Because Shannon starts with this incredibly jarring idea right out of the gate. The actual semantic meaning of a message it's entirely irrelevant to the engineering problem of transmitting it.
And that idea was just incredibly liberating for engineers, because if a communication system doesn't need to understand the poetry or, the military orders or the music it's carrying.
Right, you don't need a different pipe for a different type of message.
Exactly. You can build a single universal architecture to move literally anything. The system only cares about measuring the data and moving it from point A to point B.
Okay, so to build that universal system, Shannon basically had to completely redefine what communication actually is. He didn't just look at telephone wires or radio towers.
No, he abstracted the whole concept down to a 5-part schematic.
Yeah, let's map this out for everyone. Like, using a real-world scenario. Say you are calling a friend on a landline.
Okay, a landline, bringing it back.
Right, going vintage.
Yeah.
So first, you have an information source, which is your brain, generating the words. Then you have a transmitter. In this case, that's the microphone in the phone handset, turning your voice into an electrical current.
Right, and then the third piece is the channel. So the physical copper wire spanning the city, but crucially, the channel is also the domain of the noise source.
Ah, the noise source.
Yeah, this is where, say, a thunderstorm or just a faulty switchboard introduces static into your electrical current.
Got it. And then fourth is the receiver, right? The speaker on your friend's phone, turning that static-filled current back into sound waves.
Exactly. And finally, the destination, your friend's brain processing the sound.
So when you lay it out like that, it honestly sounds like basic plumbing.
Yeah, water goes in, flows through a pipe.
Gets a little dirty along the way, maybe, and comes out the other end. But Shannon wasn't just defining the pipe right. He was defining the water itself.
That's the huge shift. He stated that a message is simply one specific choice selected from a finite set of possible messages.
Wait, a choice.
Yeah, a choice. Because the system has to be designed to accommodate every single possible selection in that set, not just the one you happen to make.
Oh, I see. Because the engineer building the telephone network, they have no idea if you're going to say hello or goodbye or the house is on fire.
Exactly. They have to account for the uncertainty of whatever you might say. And Shannon realized that to build a better system, he had to mathematically measure that choice.
Right. And he built on some earlier work by a researcher named Ralph Hartley.
Yeah, Hartley. And Shannon argued that the most natural way to measure these choices is actually with a logarithmic function.
Okay, let's drill into the mechanics of that because math can get a little abstract. Why a logarithmic function specifically?
Well, think about physical hardware. Let's say you're building a simple computer memory using physical relays, just switches that can either be open or closed.
Okay, simple enough.
If you have one relay, you have two possible states, open or closed.
Right.
But if you add a second relay, you don't just add two more states, you multiply the possibilities. 2 relays give you 4 possible states, 3 relays give you 8 states.
Ah, so the number of possibilities grows exponentially.
Exactly. Which quickly becomes just an unwieldy way to measure system capacity. You get into massive numbers really fast.
So the logarithm fixes that.
Yeah, if we use a logarithmic scale, specifically base 2, we translate that wild exponential growth into a nice, clean, linear measurement.
Because the base 2 logarithm of 8 is 3.
Right. So 3 physical relays give you 8 possible states, which equals 3 units of measure. You get a perfect one-to-one mapping between your physical hardware and your storage capacity.
Oh, wow. That is incredibly clean. And that logarithmic base 2 gives us like the fundamental unit of the digital age, right?
Yes, the binary digit.
The bit.
The bit. A term Shannon actually credited to his colleague, J.W. Tukey.
That's a great trivia fact.
Yeah. So a device with 2 stable positions, like a relay or a flip-flop circuit, stores exactly 1 bit.
Okay, so we can measure the capacity of the system in bits.
Yeah.
But we also have to measure the message itself, right?
Mhm.
Like if communication is just a sequence of choices from a set of symbols like picking letters from an alphabet, we have to look at how we actually make those choices.
Right, because language is not just a sequence of random selections.
Well, yeah, and I want to push back a little on this idea of language as a purely statistical math game.
Yeah.
Because when I speak, I'm not, pulling words out of a hat based on mathematical probability.
Sure.
I choose a word because of its definition, its
Right.
emotional weight, the context. Like, I am actively trying to convey an intention to you.
And your intention definitely drives the broad strokes of what you're saying. But the actual mechanics of constructing a sentence, those are heavily constrained by rigid statistical rules that you don't even consciously think about.
Okay, tell me more about that.
Well, Shannon introduces this concept of a stochastic process, specifically a Markoff process.
A Markov process.
Yeah, where the choice of the next symbol depends heavily on the probabilities established by the preceding choices.
Okay, and he illustrates this so brilliantly in the paper with his approximations to English. This part blew my mind.
It's so fun.
Yeah, he starts with a zero-order approximation where he's just picking letters completely at random, and you get strings like X, F, O, M, L, R, X, K, H. Basically total gibberish.
Pure randomness.
Right. Then he moves to a first-order approximation. The letters are still chosen independently, but now they're weighted by how frequently they actually appear in the English language.
So you start seeing a lot of E's and T's and very few Z's or Q's.
Exactly. It looks slightly less alien, but then the real magic happens at the second-order approximation. This introduces diagram structure.
Right, so now the system remembers the previous letter. If it randomly selects a T, the mathematical probability that the next letter will be an H skyrockets.
Yes, because T is so common. And by the time Shannon generates word-level approximations, the sentences become structurally recognizable, even though they mean nothing.
What's one of the examples he generated?
Oh, I have it right here. It's the head in frontal attack on an English writer, that the character of this point is therefore another.
It literally sounds like someone talking in their sleep.
Ha, exactly. The grammar is completely intact. It sounds like a real sentence, even though there's absolutely zero underlying tension. The math just built it.
And that proves that a massive portion of what we say is dictated purely by the structural rules of the language itself.
Okay, so how much of our language is just structure?
Through this statistical modeling, Shannon calculates that the redundancy of the English language is roughly 50%.
50%.
Yeah, half of every paragraph you write is determined by the constraints of syntax and spelling, and only half is actually chosen freely by your intention.
Wow. Which completely explains that amazing observation he made about crossword puzzles in the paper.
Oh, yes, the crossword puzzle thing is fascinating.
Right, because crossword puzzles are entirely dependent on that specific 50% redundancy sweet spot.
Explain that for the listeners because it's such a cool concept.
Okay, so think about it. If English had zero redundancy, meaning literally any letter could logically follow any other letter in any combination, then any random grid of letters you threw together would be a valid crossword puzzle.
Right, there would be no constraints. The game wouldn't exist.
Exactly. But on the flip side, if the language had, say, 80% redundancy, the constraints would be so incredibly rigid that trying to make words intersect horizontally and vertically would just be mathematically impossible.
Yeah.
You'd never find words that fit the grid.
It's just perfect. And Shannon even compares the extremes of written English to show how this redundancy impacts compression.
Oh, like basic English versus literature.
Yeah, he looks at basic English, which is this constructed system with an 850-word vocabulary.
That is tiny.
Very tiny. And because the vocabulary is so limited, it is highly redundant. It takes many, many more words to express a complex thought.
Right.
But on the opposite end of the spectrum, you have something like James Joyce's novel, Finnegan's Wake.
Oh, man. Notoriously difficult to read.
Extremely. Because Joyce constantly invents words, he blends different languages, he massively expands the vocabulary, and by doing so, he achieves this massive compression of semantic content. The redundancy is incredibly low.
So every single word carries a ton of new information.
Exactly, which is why the text feels so dense and exhausting to process.
Okay, so this brings us to the core mechanism of measuring information itself. Because if a letter is highly predictable, like, say, a U almost always following a Q, it gives the receiver very little new information.
Right, if we know what is coming, we aren't learning anything new when it actually arrives.
So how do we measure the raw, actual information being generated?
We measure it using entropy, represented by the letter H.
Entropy, like in thermodynamics.
Exactly like that.
Yeah.
In physics, entropy measures physical disorder. Shannon adapts the concept to measure choice, uncertainty, or information. High entropy means high unpredictability.
Okay, let's use an analogy here. Think of it like a horse race.
Okay.
If I tell you the outcome of a race where one specific horse wins 99% of its races, you really aren't surprised when I tell you that horse won again.
Not at all.
Right. The uncertainty was incredibly low before the race even started, so the amount of actual information I gave you by announcing the winner is nearly zero. You basically already knew.
Right.
But if I tell you the outcome of a completely even race with 8 totally unknown horses, I am resolving a massive amount of ambiguity for you.
And therefore giving me a lot of information.
Exactly.
The philosophical shift here is just monumental. Information is not measured by the specific words you say. It is measured by the vast ocean of things you could have said but didn't. What you could have said, that is profound.
It is. Information is the exact mathematical measure of resolved ambiguity. Entropy is at its absolute maximum when all possible messages are equally likely. And when H equals 0, you are entirely certain of an outcome before it even happens, meaning absolutely no information is transmitted.
Okay, so we've quantified the message, we've quantified the system, we understand that predictability allows us to compress data, but we haven't dealt with the villain of this story yet.
The villain?
Yeah, because we have been talking about this frictionless, perfect mathematical world. But the real world is a mess, right? We have scratched CDs, electromagnetic interference, static on radio dials. What happens when the channel linking our transmitter and receiver scrambles the data?
Ah, yes. Shannon formally defines this as a noisy discrete channel. Because in the physical world, the signal that actually arrives at the receiver is a mathematical function of both the transmitted signal and the noise.
Okay, so how do we deal with that mathematically?
Shannon introduces a mechanism he calls equivocation.
Equivocation. Let's define this in practice, because I feel like this is where human intuition usually fails us.
Oh, absolutely.
Like if I'm transmitting data over a phone line and the static introduces errors exactly 1% of the time, the intuitive solution is just simple subtraction, right? We just say, okay, our effective transmission rate is 99%, and we call it a day.
And that simple subtraction completely misrepresents the physics of the problem.
Really? Why?
Because the receiver sitting at the destination doesn't have a magical map pointing out which 1% of the symbols are wrong.
Oh, right.
When an error occurs, it introduces this whole branching path of possibilities. A 0 arrives, but the receiver has to ask, wait, is this a true 0 or was it actually a 1 that the noise flipped?
Oh, wow. So the error doesn't just corrupt a single bit of data. It infects the receiver's confidence in the surrounding bits, too.
Exactly. You aren't just losing data, you are actively gaining ambiguity.
Okay, so equivocation is the formal measure of that specific ambiguity.
Mathematically, yes. It is the conditional entropy of the message, knowing the received signal. It calculates the exact amount of information that is missing due to the noise.
Let's push this to an extreme to really test it. Imagine the noise is so severe that the received signal is entirely independent of the transmitted one. Just pure random static.
Okay, pure static.
In a binary system of ones and zeros, pure random static would still result in half of the symbols matching the original message, right? Just by pure 50-50 luck.
Right. And if you used that intuitive, simple subtraction logic, you would falsely conclude you were successfully transmitting 50% of your data.
Which is obviously wrong.
Very wrong. Shannon's math proves that in a state of pure static, the equivocation rises to equal the source entropy entirely. You must subtract the entirety of the uncertainty from your transmission rate.
So the actual amount of information you are receiving is 0.
Exactly 0. You learn nothing from a static blur, even if half the bits happen to be correct just by chance, because you don't know which half.
Wow. Okay, so noise is constantly robbing us of information by driving up equivocation, which leads to this massive engineering crisis of the early 20th century. How is reliable communication even possible over long distances?
Do we just have to accept that every file will degrade?
Right. Like, does everything just get worse the further it goes?
Well, this is where Shannon delivers the ultimate breakthrough of the whole paper. He introduces channel capacity, represented by the letter C.
Channel capacity.
This is the absolute maximum possible rate of transmission for a given channel. And using C, he presents the fundamental theorem for a noisy channel.
Okay, the big one. The theorem that states if your information source generates data at a rate your entropy, H, that is less than or equal to the channel capacity C,
Right.
it is mathematically possible to encode the message so that the frequency of errors is arbitrarily small, virtually zero.
And you cannot overstate how wild this was at the time. Prior to this theorem, engineers assumed the only way to beat a noisy channel was simply to slow down.
Like having a bad phone connection. If it's staticky, you just speak incredibly slowly and you repeat every single word. I am at the store.
Exactly. But Shannon proved mathematically that you do not have to slow down.
That is mind-blowing.
You can transmit data at incredibly high speeds, right up to the speed limit of the channel capacity, and still achieve zero errors.
But wait, if I'm not slowing down, and I'm not just repeating your message over and over, I must be changing the shape of the message itself, right? How do we actually outsmart the noise at high speed?
We beat the noise through smart redundancy.
Redundancy.
Yeah. You mathematically package the data so that the relationships between the bits act as a sort of self-healing structure. Think of a simple parity check or a block code.
Okay, so instead of just sending a raw stream of data,
The transmitter chops the data into large blocks, and it appends a small mathematically derived summary, a checksum, to the end of each block.
oh, I see. So if a burst of static flips a bit in the middle of the transmission, the block arrives at the receiver, but when the receiver runs the math, the data no longer matches that checksum at the end.
Exactly. And the magic is, the math doesn't just fail. The specific way the math fails points directly to the exact bit that was flipped by the noise.
Seriously.
Yes, the receiver can mathematically deduce the error and literally flip the bit back to its original state.
That is incredible. So by exploiting that statistical predictability we discussed earlier, the redundancy basically acts as a safety net.
It does. The noise scrambles the signal, but the smart redundancy allows the receiver to perfectly rebuild the missing pieces. Now, the caveat is that if you try to transmit at a rate higher than the channel capacity C, errors become mathematically unavoidable.
Nature takes its tax.
Nature enforces a very strict tax on any excess rate, yes.
Okay, so up to this point, Shannon has mostly focused on discrete symbols, right? Telegraph taps, letters on a page, binary switches, things that exist in very distinct separate states.
Right, discrete math.
But the physical universe is mostly continuous. We communicate over continuous sound waves, radio frequencies, fluctuating voltages. How does a theory built on discrete choices scale to a continuous real-world reality?
Well, Shannon had to prove that continuous waves could be perfectly mapped into the discrete realm, and he utilized something called the sampling theorem.
A sampling theory.
Yeah, which basically dictates that any continuous signal, like a radio wave or a human voice, is fundamentally limited by its bandwidth. A wave can only fluctuate so fast within a given physical band.
Okay, so because it has a sort of speed limit, you don't actually need to capture every single microscopic slice of the wave to understand its entire shape.
Exactly. You just need to take discrete snapshots, samples, at a specific regular rate. As long as you sample the wave at a rate twice its highest frequency, those discrete snapshots contain the exact same amount of information as the entire continuous wave.
I mean, you don't lose anything.
You don't lose anything. You can reconstruct the continuous reality flawlessly from a finite set of discrete points. The discrete math perfectly, seamlessly scales to the continuous world.
Which leads us directly to the equation for the capacity of a continuous channel experiencing white thermal noise.
A very famous equation.
Yes. The formula is C equals W times the log of P plus N over N.
Right. Let's break those variables down.
Okay, so C is our channel capacity. W is the bandwidth of the physical channel. P is the average transmitter power, and N is the average noise power.
And it is just an elegant equation. I mean, it dictates the physical limits of every wireless network, every fiber optic cable, and every satellite dish on Earth today.
But looking at how those variables interact, the physical limitations become really obvious really fast.
How so?
Well, because the relationship between power and capacity is a logarithmic function, right?
Mm.
So adding more transmitter power gives you incredibly diminishing return.
Oh, absolutely.
Like, if I'm an engineer trying to push gigabit speeds over an aging cellular network, I can't just buy a massive generator and crank up the voltage on the cell tower to infinity.
No, you can't.
Because doubling the power doesn't double my capacity. It barely moves the needle. I am fighting a mathematical logarithmic curve.
Yep. To get a massive linear increase in your data rate, you can't rely on power, the P. You have to increase your bandwidth, the W in the equation.
Ah, so you need a wider pipe.
Exactly. That is why modern telecommunications companies are constantly fighting over radio spectrum allocations. You need wider physical pipes, not just louder megaphones.
That makes so much sense. You know, there's this beautiful, almost poetic paradox hidden in the quest to hit that maximum theoretical capacity too.
What's that?
Well, Shannon proved that to achieve the absolute maximum limit of transmission over a continuous channel, the encoded signal actually must statistically resemble white thermal noise.
Yes. That is such a fascinating conclusion. To reach maximum efficiency, you have to squeeze out every single drop of unnecessary redundancy from the message.
Right. Every piece of the signal must carry maximum entropy.
Because if there is any recognizable pattern left in your transmission, it means the signal is somewhat predictable.
And as we established with the horses.
Exactly. Predictability means you are carrying less information than you theoretically could be.
So perfect information, when perfectly compressed and encoded, is entirely indistinguishable from pure random static.
The ultimate signal looks exactly like the noise it is fighting against.
That is just incredible. So to kind of bring this all together, Claude Shannon took the messy, emotional, deeply human act of communication, and he distilled it into a universe of pure probability, limits, and bits.
He really did. He proved that noise is not some insurmountable physical barrier that inherently destroys our messages. Rather, noise is just an algebraic puzzle.
Right.
By defining the rigid rules of entropy, equivocation, and capacity, he gave us the exact tools to definitively solve that puzzle. Engineers no longer had to worry about what they were transmitting. They only had to focus on the mathematical architecture of the package itself.
And it is quite literally the bedrock of our reality today. The only reason you can stream a high-definition video from a server on another continent directly to a piece of glass in your pocket is because Claude Shannon separated the meaning from the math.
Absolutely.
Now, I want to leave you, the listener, with a final thought to mull over on your own as we wrap up this deep dive. We began today by marveling at how liberating it was for engineers to strip the meaning away from the problem, right? A message is just a choice. A box is just a box.
Yeah, meaning is irrelevant to delivery.
But Shannon also proved that all human language, all of our poetry, our jokes, our deepest confessions can be mapped down to statistical probabilities and structural redundancy.
Which raises a really profound question at the nature of thought itself.
Exactly. If a machine can flawlessly map the statistical structure of our language,
Yeah.
moving far beyond Shannon's second or third order approximations and scaling up to a 1,000th order approximation.
Right.
If an artificial intelligence can perfectly predict what word will resolve our ambiguity and structure a sentence exactly as a human would, at what point does that machine stop merely calculating probabilities? At what point does the generation of that perfect statistical structure become the generation of actual meaning?
It really makes you wonder.
If the postal worker learns to perfectly mimic your handwriting, flawlessly fold the paper, and chemically replicate the tears on the page, does it even matter who sealed the box?